In 1989, inside a quiet laboratory at the University of Utah, two chemists stood in front of cameras and claimed something that sounded impossible. Martin Fleischmann and Stanley Pons announced they had achieved nuclear fusion. At room temperature, no billion-dollar reactor. No sun-level heat, just a tabletop experiment, a metal electrode, and a glass cell filled with heavy water. The data, they said, showed excess heat far more than any chemical reaction could produce. If true, it meant nearly limitless clean energy. The announcement wasn't a rumor. It was documented, televised, and formally presented. And within days, laboratories around the world began racing to reproduce what might have been the most important scientific breakthrough of the century. There was just one problem. No one could make it happen again. It began as a routine electrochemistry setup. A simple glass cell, heavy water. A strip of palladium metal submerged like nothing extraordinary was about to happen. But inside that metal, something strange was unfolding. Fleischmann and Pons reported that as electric current passed through the cell, the palladium absorbed large amounts of deuterium, an isotope of hydrogen, packing it tightly into its atomic structure. Then the temperature began to climb. Not gradually. Not predictably. The instruments showed excess heat, sustained heat that couldn't be explained by chemistry alone. According to their measurements, the energy output was significantly higher than the electrical input. In nuclear physics, that imbalance means only one thing: a reaction beyond ordinary matter. They repeated the measurements, checked the calibration, ran the numbers again. The readings held. On paper, the impossible had just been observed. This wasn't a late-night experiment scribbled in a private notebook. The results were documented, recorded, and presented under institutional authority. The press conference at the University of Utah was formal. University officials stood beside Martin Fleischmann and Stanley Pons, signaling confidence. Internal reports detailed calorimetry data, input-output, energy measurements, and experimental conditions. The numbers were specific. The claims were clear. Soon after, a paper was submitted to the Journal of Electroanalytical Chemistry, outlining the methodology. The work wasn't anonymous. It carried names, affiliations, and reputations built over decades. Governments took notice. Funding discussions began almost immediately. If this was real, it would rewrite physics and reshape global energy overnight. Nothing about it looked like a hoax. It looked official. It looked measured. And that's exactly why the scientific world reacted so fast. Within days, laboratories across the United States, Europe, and Japan began rebuilding the experiment. Palladium rods were ordered in bulk. Heavy water supplies tightened. Electrochemical cells flickered on in universities that had never spoken to each other before. If two chemists in Utah could produce excess heat, others should see it too. At places like MIT and California Institute of Technology, physicists and chemists set up near-identical systems. Same materials, same current levels, same reported conditions. They watched their thermometers carefully. Or spaced 10 days. Some teams reported small anomalies, tiny bursts of unexplained heat. Others saw absolutely nothing. No surplus energy, no nuclear signatures, no radiation levels consistent with fusion. The numbers refused to align, and what should have been a straightforward confirmation was quickly turning into something far more unsettling. What started as excitement slowly turned into pressure. By the summer of 1989, more than a dozen major research centers had tried to replicate the experiment. Teams adjusted electrode purity. They refined calorimetry methods. They modified current densities. Some even recreated the setup line by line from the original paper. Still, the results split in two. A few groups reported fleeting signs of excess heat, never stable, never fully measurable. Most reported nothing at all. And in nuclear physics, inconsistency is everything. A real reaction doesn't perform on command one day and vanish the next. At MIT, internal debates grew tense. At California Institute of Technology, skepticism sharpened into public criticism. If you're enjoying this unfolding investigation, stay with me, because the real turning point wasn't the failed experiments. It was what happened behind the scenes, in the data itself. In science, replication isn't optional. It's the filter that separates discovery from illusion, and that's where everything began to fracture. As independent teams published their findings, the pattern became uncomfortable. The vast majority reported no measurable excess heat. Even more troubling, there were no consistent nuclear byproducts. No detectable neutrons, no gamma radiation, nothing that normally accompanies fusion. At the same time, scrutiny turned toward the original measurements. Calorimetry, the method used to calculate excess heat, is notoriously sensitive. Small calibration errors can create large illusions. Then came a deeper blow. Researchers at MIT published data suggesting the heat curves didn't support the dramatic conclusions being claimed. The conversation shifted overnight. This was no longer about proving cold fusion real. It was about whether the original evidence had ever truly shown it at all. As criticism mounted, the debate didn't disappear, it evolved. Some researchers argued that replication failures didn't disprove the phenomenon. They suggested the key might lie in something subtle. The microscopic structure of palladium itself. Tiny cracks, impurities, atomic-level loading ratios of conditions so precise they were nearly impossible to reproduce consistently. Others proposed unknown solid-state effects, exotic interactions happening inside the metal lattice. Outside traditional nuclear theory, if fusion was occurring, maybe it wasn't behaving the way textbooks predicted. Supporters pointed to scattered reports of tritium, traces, and brief neutron signals from independent labs. Not strong enough to convince the mainstream, but not zero either. The phenomenon hovered in a strange space, never confirmed, never fully erased. It was as if the experiment worked, but only when it felt like it, and that ambiguity kept the door open far longer than anyone expected. As the noise grew louder, some researchers stopped arguing about theory and went back to something simpler. The graphs buried inside the early reports were subtle irregularities in the heat, curves of small shifts in baseline calibration, slight timing offsets between input power and measured output. Nothing dramatic at first glance, but in calorimetry, tiny mismatches can create the illusion of excess energy. At MIT, reanalysis suggested that when corrected for calibration drift, the excess heat largely disappeared. Supporters countered, accusing critics of selectively presenting data. Suddenly, the battle wasn't just experimental, it was interpretative. The same dataset was being read in two completely different ways. And the unsettling part, both sides believed the numbers were on their side. By the end of 1989, the scientific establishment had largely made up its mind. Panels convened. Reviews were published. Funding evaporated. The consensus was blunt. There was no convincing evidence that room temperature fusion had occurred. But consensus is not the same as closure. Were Martin Fleischmann and Stanley Pons committing fraud? No formal investigation ever proved fabrication. Sloppiness. Possibly overinterpretation under global pressure. Very likely. Yet a small group of researchers refused to walk away. They continued studying what they now called low-energy nuclear reactions, arguing that anomalies persisted, just not in a controllable way. So the story settled into an uneasy middle ground. Not a proven breakthrough, not a confirmed hoax. Just a documented claim that shook the scientific world and never fully disappeared. In the end, cold fusion didn't power the world. The initial claim made by Martin Fleischmann and Stanley Pons collapsed under the weight of replication failures, institutional criticism, and missing nuclear evidence. By the early 1990s, mainstream science had moved on, but the record never vanished. The press conference happened. The data was published. The global rush to reproduce it was real. Entire laboratories redirected resources in response to one announcement. For a brief moment, the laws of physics seemed negotiable, and that's the part that lingers. Cold fusion became a case study in how science actually works, not as a straight path to truth, but as a brutal stress test. Extraordinary claims are allowed. They're investigated. They're challenged. And if they can't survive repetition, they fade. Yet even today, small research groups quietly revisit the question under new names and new methods. Because the most uncomfortable possibility isn't that the experiment failed. It's that under conditions we still don't fully understand, something unusual may have happened in that glass cell in 1989. and that uncertainty, that thin space between error and undiscovered, physics is why this documented phenomenon still refuses to disappear.